Hi, this is Algebra 1, Lesson 3-2, Linear Functions. In this lesson, you'll be able to identify, evaluate, graph, and write linear equations. Okay, you will also use function notation. You will graph a linear function and relate the domain of a function to its graph. And you will also interpret functions represented by graphs, tables, verbal descriptions, and function notation in terms of a context. Let's look at explore and reason. The flow chart shows the steps of a math puzzle. Flow chart is any chart that has an arrow and there's a flow of reasoning shown in the chart. Okay, so part A, try to puzzle with 6 different integers. So first, think of a number. You multiply that number by 9. And then you subtract your original number. You divide that number by 4. Okay? Try that with 6 different integers. Integers are positive and negative counting numbers, including 0. So let's record some of your thoughts. Okay, record your integers. So if you think of a number 2, okay, think of a number 2, you multiply that number by 9, and then you subtract your original number, and then you divide this whole thing by 4. Okay, so 18 minus 2 and 16 divided by 4 is 4. What about 3? 3 times 9 minus 3, all divided by 4. Okay, 27 minus 3, 24 divided by 4 is 6. Okay, what about some negative numbers? Negative 2 times 9 minus 2 divided by 4, right? So negative 18 plus 2 is negative 16 divided by 4 is negative 4. Okay. What about 5? 5 times 9 minus 5 divided by 4. Okay. 45 minus 5 is 40. Divided by 4 is 10. 1, 2, 3, 4, 5, 6. So you do two more different integers. Okay. You can record each number you try and the result. I'm going to do 10 next. And I have 90 minus 10, 80 divided by 4 is 20. Okay. And then negative 1 times 9 minus 1 is plus 1. And so negative 9 plus 1 is negative 8 divided by 4 is negative 2. Okay. Yeah, and then you're gonna make a prediction about what the final number will be for any number. Do you see any patterns? Yes, look at your patterns. You have, if you have 2, you get 4 as an answer. 3, you get 6 as an answer. Negative 2, negative 4. 5, 10. 10, 20. Negative 1, negative 2. Do you see the pattern there? Yeah. If you put any number in, your final number is always twice the original number. Okay. Would your prediction be true for all numbers? Yes. Not just these 6 numbers, but yes, because we figured out the pattern, right? Because no matter what number you choose, you're multiplying it by 8 and then dividing it by, dividing that quantity by 4. Wait, It's not 8. It's multiply the number by 9 divided by 4, which is equivalent to multiplying the original number by 2. Right? Because if you multiply your number by 9 and then you subtract your original number, that really means you're multiplying it by 8 and then dividing it by 4, which means you're multiplying it by 2. So let's record that. Because when you multiply a number, any number, by 9 and subtract the number, which is going to be the same, it's like multiplying it by 8. Okay, and if you divide that by 4, it's always going to be twice the original number, right? So let's think about this essential question. How can you identify a linear function? Okay. Example 1. Evaluate functions in function notation. Part A. How can you represent a function value, a function rule? Okay, first write the equation y equals 5x plus 1 using function notation. Okay, this is an equation of a line, right? You've learned equations of different forms of linear equations, okay? You already know how to write the equation. But what's a function notation? Okay, function notation. We're gonna read later. But first, remember that function is a rule that is an input or an element in the domain and maps it into an output or an element in the range. So you need a domain and the range, and each of the domain has exactly one value of output or value in the range. Okay, function notation is a method for writing variables as a function of other variables. The variable y becomes a function of x, meaning the variable x is used to find the value of y. And that makes sense because x usually represents the input, y is going to be the output. This helps distinguish between different functions. You can use the relationship between variables to solve problems and make predictions. Okay, so this is the input, the x value goes in, and then you use the equation to solve for the variable y, and then you get the output, which is your function of your x. Okay, so this f of x, you're going to read it as f of x. That parentheses means of. Okay, so you don't need to say parentheses every time. You're going to say f of x. The function f is defined in function notation by f of x equals the equation. Okay, instead of y, you're really writing f of x to represent a function. Okay, they're very similar. They're pretty much the same thing, but it's different. Y, if it's a y, it's called an equation. If you have a f of x, it's called a function. Okay, you have proved, there's an implication that the equation makes a function. There are a lot of equations that are not considered functions. Okay, so that's the difference. Part B. What is the value of g of x equals 5x plus 1 when x is equal to 3? Yes, it doesn't always have to be f. Sometimes it's g. Okay, very commonly used for function notation would be both f and g, but mostly f. But g is also used very commonly. Okay, so evaluate g of x equals 5x plus 1 for x equals 3. You substitute 3 into the equation for x. Okay, you plug in 3 instead of x. And then you substitute 5 times 3. You solve this equation. 5 times 3 plus 1. That's 15 plus 1, which is 16. And that's your output. Input, output, and that's your equation, which does all the work. Okay. So if g of x is equal to 5x plus 1, then g of 3 is equal to 16. This is how you write your final answer. What is the value of g of x when x is equal to 3? G of 3, which means when x is equal to 3 for the function g of x, it's going to be equal to 16. Okay? Let's look at try it number 1. Evaluate each function for x equals 4. G of x is equal to negative 2x minus 3. So you're going to use that equation and figure out what your output is when you put an input of 4. Okay, so negative 2 times x minus 3 would be negative 8 minus 3, and that's negative 11. So your output is negative 11. How do you write that as an answer in function notation? G of 4 is equal to negative 11 would be the correct notation and the answer. Part B, h of x. Yes, you could also have h and other many letters. Okay, equals 7x plus 15. So 7 times 4 plus 15 is 28 plus 15. And that's really 43. Right? So then you can rewrite this as h of 4 is equal to 43. That is your answer. Okay, it means when x is equal to 4 in the function h of x, then the function value will be equal to 43. Okay. Example 2. Write a linear function rule. The cost to make 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? Step 1, you're going to examine the relationship between the values in the table. Okay, we got 1, 2, 3, 4. The domain values seem to be increasing by 1. The cost, 17, 32, 47, 62, seems that they are also increasing by 15 at the same rate. Okay, the relationship is linear. Step 2, write a function using slope-intercept form for the rule. Okay, using slope-intercept form, y equals mx plus b, except your y is going to be written with f of x. Your slope is 15. For every increase of your number, you're going to multiply that by 15 plus whatever you're starting with. Step 3, find the value of b. What is your y-intercept? What is your cost when the number of bracelets are 0? Right? You can substitute any ordered pair, which could be 1, 17, 2, 32, 3, 47, 4, 62. Just pick any point. Usually, the smaller the number is, it's easier to calculate. So pick 1, 17 and solve for b. B is 2. Okay, so if the number of bracelets is 0, the cost is still $2. Okay. You can use the function f of x equals 15x plus 2 to determine the cost to make any number of bracelets. This is your equation, right? So, and this function is a linear function because the rule 15x plus 2 is the same as the rule of a linear equation. It fits the linear equation, okay? So if you see the rule that has any kind of form matching with the linear equations that we learned last topic, then it's a linear function. Let's try number 2, A and B. Write a linear function for the data in each table using function notation. Okay, really, you're writing the equation down, probably using slope-intercept form. But instead of using y, you're gonna write using f of x. Okay, come back when you're ready. All right, part A. Your x is increasing by 1. Your y is increasing by 6.5, right? And so what is your slope? 6.5 over 1, okay? Which is 6.5, because change of y, your slope is change of y over change in x. How much you rise over how much you run, okay? Always remember that slope. And then you're gonna use your slope-intercept form, mx plus b. Your m is 6.5 x plus b. Pick a point, okay? I am not gonna deal with decimals, so I'm gonna pick 2, 13. So you have 13 is equal to 6.5 times 2 plus b. We're gonna solve for b in order to figure out your y-intercept for the equation. 6.5 times 2 is 13. And then in order for 13 to equal to 13, your b has to be 0. So what's your equation? Your equation is y equals 6.5x plus 0, which is just 6.5x. So your f of x is 6.5x, and that is your final answer for part A. In the same way, part B. For every change in y, how much is your change for x? That is your slope. So your y, you're adding 3 each time. Every time you add 1 for your x, right? So 3 over 1 is going to be your change of slope, which is just 3, right? So then use your slope-intercept form, 3x plus b, and pick a point. 1, 1 sounds nice. 1 equals 3 times 1 plus b. And so b is equal to 1 minus 3, which is negative 2. So your equation is 3x minus 2, plugging in your slope and y-intercept, right? So then your f of x, your function notation should be 3x minus 2. Okay. Let's look at example 3 on the next page. Analyze a linear function. Tamika records the outside temperature at 6 a.m. The outside temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? Okay, now we have a word problem, but don't freak out. We're going to take step by step. Okay, step 1, write a function that models the situation. How do you write a function that models the situation? Identify the information. Okay, the outside temperature increases by 2 degrees Fahrenheit, so that is your slope. That is your rate of how much it increases, right, for every hour. So 2 degrees Fahrenheit per every hour, 1 hour means 2 Fahrenheit per hour, and that's your slope. Okay. And then that's for the next 6 hours. Okay. And your y-intercept is where you're starting from, right? When your x is 0, that means when your time is at the starting point, 0, what is your temperature, right? It started at right here, -3. So that is your y-intercept. Your slope is 2, y-intercept is -3. So your function should be f of x is equal to 2x minus 3. Sketch a graph of the function, step 2. And then you're going to find the value of y when x is equal to 8. You already know how to sketch a graph of the function. Pick the y-intercept and then count your slope to figure out the next point, and then the next point, and then the next point. Okay, go up to over 1, up to over 1. Okay, so when x is 8, you can see that it's going to be at 13 degrees Fahrenheit. Or you could plug it into your function algebra, and you can solve it algebraically, and that's going to be 13 as well. Okay, it's a line. A linear function is a function whose graph is a line. Okay, linear equation, linear function, they're pretty much similar things, but function has to be a function. The equation could be anything, any equation that graphs a line without being a function. Okay. Part B, does using a linear function realistically represent the temperature for the domain of 0, x is greater than 0, less than 24? This graph has a slope of 2, which represents the temperature rising 2 degrees Fahrenheit each hour. However, when the sun sets, it's unlikely that the temperature will continue to rise. So the linear function is realistic for only a portion of a day, specifically 6 hours, right? They said it increases 2 degrees Fahrenheit every hour for the next 6 hours. So after that, it's going to be different. So it's not going to be a linear function after that, the same function after that. Let's try number 3A and B. We're going to sketch the graph of each function. It's same. It's the same way how you would graph a linear equation. Okay, it's a linear function, which means it's a function. But the way how to sketch it, it's the same thing. You can recognize this form as what kind of linear equation? Which form is this? The slope-intercept form. We have the slope and the intercept. So start with the slope, the intercept, y-intercept, and count the slopes to sketch the graph of it. For part A, what is your y-intercept? Y-intercept is 1, and your x and your slope is -1. Okay, -1x, right? So then in your graph, your function was -1x plus 1. So your y-intercept is 1, slope is -1. So you start with 1 here. And then you count your slope. -1, go down 1, and then +1 over 1. Go down 1 over 1. And then if you want to go up 1, you go left once. Okay, up 1, left once. And so on. So using these points, you're gonna draw a line through these points, and that should be your line of f of x. Okay, you need to have one of the y-intercept and a negative slope going down 1 by 1. Okay, that's 3A. All right, let's look at 3B. What is the y-intercept for this one? 1. What is your slope? 3. Okay, so let's erase this and graph a new one. Whoops. Okay, your function was g of x, 3x plus 1. Okay, that's 3b. So your y-intercept is 1. Your slope is 3. 1, 2, 3. 3 over 1, And 1, 2, 3 over 1. Wait, I counted 2. Just kidding. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, go down 3 and then go left 1 would be your next point for your left side of the equation. So once you get enough points, you can connect these dots. Okay, and this is g of x. Okay. All right, so that's a positive slope. It looks like it's going up from left to right. All right, going to the next example. Example 4, use linear functions to solve problems. A chairlift starts 0.5 miles above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? Okay, chairlift travels 6 miles per hour. So there you go. That's your slope. It takes 15 minutes to reach the top. So that's your constraint, okay? Your time is going to be 0 to 15 minutes. And 0.5 miles from the base. Okay, these are some important information. So looking at taking these information, we're going to write a linear function to represent the distance the chairlift travels from the base of the mountain. Okay, we're going to let t be time in minutes. Okay, instead of x, we're going to use t. And t is your domain now. Okay, so 6 miles per hour is your speed. And if we multiply that by 1 hour over 60 minutes, because that's the conversion rate for hour and minutes, hours to minutes, right? So our new speed could be 0.1 mile per minute. Why are we doing this? Because we need to match all the units in the equation, okay? We have two variables. We have time and then the distance traveled. And the distance traveled would be miles, okay? But time, we're gonna write times in minutes. So, so that we can use this information 15 minutes to substitute x values for inputs, okay? So we're gonna change it from hours to minutes and figure out our new slope, which doesn't change. Slope is still 6 miles per hour, but in other conversion, we can say, oh, it's gonna be 0.1 miles per minute, okay? That's our same slope. So write the equation, d of t, d is your output, which is your range of your domain, is how you write the function notation. D of t is equal to rate of the chairlift, your slope, 0.1 miles per minute, and time traveling, which is just t, plus distance from the base, 0.5 is where you're starting from, okay? So then we've figured out our formula. We're gonna compute the distance of the chairlift from the base of the mountain at any time. So you can graph from 0.5, that's 0.5, and going up 1, that's 6, up 1 and over every mile. So that's here, this is 1 mile, that's 2 mile, that's 3 mile and 4. And that's 6 miles, 10, and so on. So you can figure out your first y-intercept just by looking at the equation and then count your slope, okay? 0.1 just means 0.1 over 1. Or you could think of it as 1 over 10, but here you're not just going to go up 1 and then go over 10. That could be like too big of a leap. If you want to count 1 by 1, you could count 0.1 over 1, or yeah, you could just count 1 and then over 10. But just make sure you count the right blocks for 1, because these grid lines are in decimals, okay, 0.2. All right, And so after 10 minutes, the chairlift will be 1.5 miles up the mountain because 10 is right here. 10 comma 1.5, okay? So that's our answer. Let's try number 4. In example 4, how would the function graph an equation change if the speed is 4 miles per hour instead of 6 miles per hour? What's the effect on the domain? Right? So everything's the same except the speed. We're gonna start at the same point, but we're gonna have to convert our speed into miles per minute again. Okay, so we got a new speed 4 miles per hour. So converting that to minutes, we got 1 hour. We got 60 minutes in 1 hour. So we are going to multiply hour over 60 minutes so that we can get rid of these hours. And then we have 4 over 60 miles per minute. In decimals, let's see. In decimals, it's going to be 0.06 repeated miles per minute, or you can write it in a simplified fraction, 1 over 15 miles per minute. Okay, so 1 mile for every 15 minutes. You're going 1 mile every 15 minutes. Okay, that's your speed. So then you write the new equation again. Wait, it's not y, right? We're gonna use t for time and then d for distance. So d of t is equal to 1 over 15 t plus 0.5. Okay. So that is your function. And then you're gonna figure out how many minutes would it take to get to your up in the mountain, right? So, or 10 minutes. So let's explain that. The function d of t would still relate the distance traveled from the base of the mountain to the number of minutes the chairlift travels, but the equation would change to d of t is equal to 1 over 15t plus 0.5. Okay, the starting point should be the same, but if you graph it, it's gonna be going up slower. Okay, so the graph has a less steep slope. Okay, and the domain. Talk about domain. Domain will change from 15 minutes to get to 2 miles, right? To how many? How long does it take for you to get to 2 miles? Well, use the equation to figure that out. Right? And then you have 1.5 is equal to t over 15. So multiply 15 on both sides. That's going to be 22.5 equals t. Okay, so the domain will change from you're gonna say t. The 0 is between 15 to t big bar. That just means we're talking about t, not the distance. Okay, 0 less than equal to t less than equal to 22.5. Okay, so it just takes more time to get to the end. All right, so let's summarize our lesson. We've seen linear function representations. Linear functions are represented by words, rules, tables, or graphs. We looked at all the different types of representations. Function notations tells us the name of the function and the input variable. So remember that you read this function notation as f of x. And whatever the variables are, it's your output of your input. Okay, and then you write the rules for that. So you can represent using the table. These are ordered pairs. And the graph, you can plot the points and graph a linear equation. All right, that was topic 3, lesson 2, linear function representations. And I'll see you in the next lesson.